So in this video we're going to be solving for a mass on an inclined plane given a coefficient of static and kinetic friction, and the question is, does the mass accelerate down the plane if it starts at rest, and if so, at what rate? So we have a 6 kilogram mass is placed on an inclined plane that is at an angle of 45 degrees. The coefficient of static friction between the mass and the plane is 0.600 and the coefficient of kinetic friction is 0.450. Does the mass accelerate down the plane? If so, at what rate? The first thing we want to do, as always, is we want to draw a picture of what's going on. So here's my inclined plane. Here's our 45-degree angle. Here's our mass on the plane. I'm going to pick my coordinate axes to be parallel to the plane for the x-axis and perpendicular for the y-axis. If you're not familiar with that, you should look at the video on Introduction to Inclined Planes. I know that I'm going to have a weight that points towards the earth. I'm going to have a force of friction that's up the plane, because if it slides down the plane, the force of friction wants to oppose that motion, and I'm going to have a normal force out of the plane. At this point, I recognize that my weight is not part of this axis, and I'm going to just redraw this axis in an orientation that's easy for me to look at. So I've essentially rotated it, and now my force of friction appears to point to the right. That right is up the plane. My normal force points out of the plane, and I've got my weight, which points neither on this axis or this axis, which means we have to resolve it. At this point, we're familiar with the idea that we have two components to that weight. We have a y component and an x component. The y component is the one that points into the plane. The x component is the one that points down the plane or parallel to the plane. It's the one that makes things go down the incline. We know now from our other video that the x component is going to be FG sine of theta. Here we go, sine is opposite over hypotenuse. FGY is going to be FG cosine of theta, because cosine means adjacent. And one of my wonderful students drew a picture of himself, or of another student, I'm not really sure. But we'll leave it there for now, because it's already there. Alright, so if I take this diagram and I redraw it down here and I ignore this FG, because now that I have the y and x component of FG, I no longer need the actual weight there. This FGX and this FGY account for the actual weight of the item, the force due to gravity. I'm going to call my right positive and I'm going to call my up positive for my two axes. And now I'm going to try to solve this problem. Now that I have everything broken down, I can separate into my x-axis and my y-axis, and I can start writing down everything I know. Well, first of all, I'm not given a weight. I'm given a mass. So I need to find my weight. I'm going to multiply my mass times my acceleration due to gravity, 9.81 meters per second squared. Now, I seem to have written negative 9.81 meters per second squared. That's not really relevant right now because the acceleration due to gravity points directly down, which, if we look at this diagram, is at this angle. It's not on either of these axes. So to call it negative 9.81 meters per second squared, not really relevant. After I transform or solve for the components of FGX and FGY, and I see which directions they act, I will assign them positive or negative signs. So finding a positive or negative sign of this FG is actually irrelevant right now. And I'm sorry that I put it in there like that. So anyway, we go ahead and we find our weight, and we find that it is 58.9 newtons. I just carried through that negative. Again, it's not really important right now. So if I wanted to find my FGX, I'm just going to plug into my equation that says FGX equals FG sine of theta. So 58.9 newtons times sine of 45 degrees. And right now I'm just looking for a magnitude, so I didn't put a negative sign. It doesn't really matter. I'm going to assign my direction later. I find 41.6 newtons. I think you already know that because we are at 45 degrees, we're going to find the same magnitude in our x direction as we do in our y direction, because a 45, 45, 90 triangle has two similar sides, or two sides of the same length rather, and sine of 45 and cosine of 45 are the same thing. So now we can break this up into our x and our y. When we break it up into our x and our y, we want to find the net force in each direction. And when we say net force, we literally mean every single force. So in the y direction, I look in my y direction, I see my weight, I see my normal force, and that's every force. I know I'm not accelerating my y direction. I know I'm at a net force of 0 newtons, so it's easy enough to plug in my value of FGY. And you'll see here that for my FGY, I did make it negative, because when I went on my axes, I made the direction of my normal force positive. So I solve for my normal force, and I'm going to find 41.6 newtons for my normal force. And there's nothing more we can do in the y direction. We're all done. Everything's done over here. So now I'm going to go over here. I'm going to go to my x direction. In my x direction, I know that my net force is all of the forces, which is my x component of gravity, or my parallel component of gravity, plus my force of friction. And I don't know my force of friction yet. I don't know my net force because the question is, does it accelerate? I do know my FGX, and I do have a way to find the force of friction given this equation. So for FGX, I've decided to call the left side negative, so negative 41.6 newtons, and I need to find the force of friction. First, I need to know if it accelerates. So I need to find the force of friction for static friction, and if we overcome static friction, we accelerate, and if we don't, we stay at rest. So here we go. Here's our equation. Force of friction is equal to mu Fn. If I'm looking for static friction, I'll plug in my static coefficient. If I'm looking for kinetic friction, I will plug in my kinetic coefficient. So, to find my force of friction for static friction, I'll plug in 0.600 times my normal force of 41.6 newtons. For my kinetic, I will plug in 0.450, which is the static coefficient, or the kinetic coefficient, times, again, our normal force, this equation right here. Plug it in a calculator. I'll find 25 newtons is my static force of friction. That's the maximum possible force of friction that we can have. The kinetic is 18.72. Sig figs, that would be 18.7 newtons. And now what I'm going to do is I'm going to look over here. I'm sorry, I forgot the newtons on my 18.72. And I'm going to see right here that the force of gravity pulling me down this incline, this FGX, is greater than our static friction could possibly be. Since it's greater, we're going to overcome that static friction. We're going to start moving. Since I know we're going to start moving, I know I need to use kinetic friction, because once we're in motion, it's kinetic. Again, I forgot the newton here, I'm sorry. So I have negative 41.6 newtons, meaning 41.6 newtons down the plane, plus 18.7 newtons up the plane, that's the friction. I find my net force. I find a net force of negative 22.9 newtons, in other words, still down the plane. Finally, to find the acceleration, I just need to divide my net force by my mass. So negative 22.9 newtons divided by 6.00 kilograms. and I find an acceleration of, drumroll, negative 3.82 meters per second squared. That negative, because it's in the same direction as the x component of gravity, the parallel component of gravity, the component of gravity that makes us go down the plane. So this negative acceleration is consistent. We put something on an incline, it wants to go down the incline.